is Building Resilient Distributed Systems Through Event Sourcing. My name's Tom Wheeler, and I put this slide up here to tell you a little bit about my background. Currently, I work as a principal curriculum developer at Temporal Technologies, so I'm building training material to teach people how to use our APIs and develop applications with our platform. But I want you to see, like, my background is not just as in technical education. I'm a practitioner as well. So I've been principal software engineer at Object Computing. I worked at WebMD as a software engineer. Before that, I was a programmer analyst at A.G. Edwards. And so I have built distributed systems throughout my career. Currently, I'm teaching people about them, but I've built them. The problems that I'm going to describe and the solutions to them are meaningful to me because I've been there. I've had to design these systems. I've been paged at 2 in the morning when things go wrong. And so nothing makes you appreciate resiliency like getting paged at 2 in the morning and having to crawl out of your warm bed to diagnose and ultimately come up with a solution for a problem. But I'm going to begin with a little bit of history. Back in the day being however you want to define it, but if you think back long enough before microservices and those sort of architectural movements have come along, when everything ran on a single computer, you build a business application, it ran on a single computer. You divided your business logic up into functions, or if you're living on the bleeding edge, methods perhaps. And you invoked the business logic by making function calls and method calls. It was all internal to the computer. You didn't have a network to contend with, and you had everything in one database, which means you could rely on database transactions. You could ensure the consistency of your data because you had that developer productivity benefit of database transactions. But in reality, it wasn't all good. There were a lot of problems with this approach. Notably, you had very limited scalability. There's only so large you can make a single computer. A single computer is, by its very nature, a single point of failure. So that limits availability. And the tools that were available at the time limited the velocity of being able to develop things. And so there were good things and bad things about the old times. Eventually, we had a bright idea about how we could address some of these concerns. Instead of trying to do everything on one computer, let's use a bunch of computers together that are working together towards a single problem, and then they communicate over a network. And so you distribute the logic across a bunch of different computers. And my introduction to that kind of thing came along back when I was working at a brokerage company, my first full-time job as a programmer. And I was on the scary internet development team, which frightened all the brokers that were used to green screens and mainframes and that kind of thing. So our system of record was a Bull mainframe, and all the market data, the research reports, all that kind of stuff, it was published to the Bull mainframe. And we had developed the intranet because we were like, people don't in this day and age want to look at things through a green screen. They just want to use a web browser. The internet was taking off, and so they want to use a web browser to read that kind of stuff. So we built an intranet, and components of that were running on a Sun server. But we had to publish everything that got published to this intranet also eventually had to make its way back to the mainframe. And I say eventually, there were like compliance requirements about how quick it had to be, and it couldn't fail. Failure was not an option. So I had to write the system that made sure that everything that got published to our intranet ultimately wound up on the mainframe, which is, I'm leaving out a lot of complexity, but there's a lot of complexity there. For one, even though this machine was maybe 50 or 100 feet away from the mainframe, they were in the same data center, in the same building. They were on different network segments, and the Bull mainframe used different network protocols than the Sun, which used standard TCP/IP. And I couldn't actually talk to the mainframe directly for reasons that were never clear to me, but there was this intermediary, this tandem nonstop computer, maybe some of you remember those, that sat in the middle, and it sort of acted as a buffer. So I would send stories to the tandem. There was a service running there that would batch them up and publish them back to the mainframe. And then, so I wrote all the stuff that was running on the Sun machine to make sure that they got published to the tandem got them published to the Bull. But there were a lot of problems that happened. For example, I would call the service running on the tandem, and despite the name nonstop, sometimes, in fact, that service did stop, and it wasn't available. So I'd try to make a connection, no socket connection, and so I'd have to wait, and eventually I'd have to call the administrator and say, hey, restart your service. Sometimes I would make a call, but the tandem was busy doing other things, so it'd be very slow to respond. Sometimes it would respond, but it'd give me an error message back, so I couldn't actually uh, send any information to it. So I had to deal with all these sort of outages that occurred. And so I went through this path to enlightenment about how we can address these kind of things. So some requests, as I mentioned, failed because the service was down or because it was overloaded. So I thought, okay, where I'm making a call, I'm going to put it in a for loop. And so I'm just going to keep iterating until I'll keep repeating this call until it eventually succeeds. And then we learn about idempotency because you didn't want it to get published twice. And so we put idempotency keys in there. The next thing I did, after getting an angry phone call from the administrator of the tandem who said, hey, the service is overloaded and you're making it worse because you keep hitting it, making all these calls. I said, okay, well, I'll put a delay between each call. And I improved that eventually by putting a back-off coefficient. The delay got longer through each successive call, and that improved things a little bit. Then sometimes, as I mentioned, I'd make a call and I'd be waiting for a response, and the response never came. Like, it was accepting the socket connection, but it never actually did anything. So then I added code, and so my client would be hung at that point, and in order to make progress and move on to the next thing, I had to write code to handle timeouts. So I added that. This eventually, like, we went through enough iterations where it went from not working all that well to being fairly reliable, but I'm not even sure that I'd call it a success because my code got longer, it got more complicated, it became harder to understand, and I couldn't just pass it off to the next person, the next sucker that got hired. You know, I wanted to move off to another project, but there I was stuck maintaining that. And probably many of you will recognize that saga because you've been through it yourself. You know, if I was doing this, you know, in the context of the Sun machine and publishing stories using protocols that we made up, but you know, microservices, you've got the same sort of situation in modern times where you're trying to call a service and the service is unavailable or the network is down. There's any number of things that could prevent you from being able to accomplish your goal. Ultimately, though, the goal is to achieve resiliency in the application. And the way that I define that is being able to withstand or recover from adverse conditions. Taking a step back, though, as software developers, we spend our days writing code, thinking about code, designing it, ultimately writing it. But the applications that we write, by writing that code, they don't actually do anything by themselves. You can write code, you know, to calculate a number, but is it going to calculate the number? No, it just sits there. The thing that you have to give it for it to be able to achieve its goal is execution. The code is static. So execution is what brings code to life. Unfortunately for us, though, execution is also what makes failure possible. You know, so if you think about the code you write, all the code you write is truly bug-free until the moment you run it. You know, it's how do you make a computer secure? Well, you encase it in concrete and put it inside a locked closet with armed guards standing outside. So if you never run the code, there's never an opportunity for failure. But as soon as you run the code, that's where failure becomes a problem. So I mentioned that what we're trying to do is make our code be able to withstand or recover from adverse conditions. Some of those things, like the one I told you, are relatively straightforward to handle because they're problems within the execution. For example, if you make a network request and it fails or it times out, you can retry it. Hopefully you're calling a service that's idempotent so it doesn't cause problems with the state. Ideally, you put a delay in there so you don't anger the person responsible for that service, but it's pretty straightforward how you handle that. A bigger problem, though, is when the execution terminates prematurely. And there's a lot of reasons that that can happen. One is there's a bug in your code and the application crashes. That's a problem, for example, if you're using C or C++ or some language like that, and you've got a problem with your memory and you forgot to allocate the right thing, and the application crashes. Another problem, though, is there's a bug in the operating system. Your code is running inside the operating system, and if there's a bug in the OS and you get the blue screen of death, then that halts your program and you're out of luck. It could also be that the hardware that you're running on fails. The hard disk wears out, the memory goes bad, the CPU burns out because the fan got blocked with dust or something like that. Could be that there's a power outage or there's routine maintenance that's taking place to the system. It's Patch Tuesday and the administrator is rebooting it. There's all sorts of reasons that your execution could terminate prematurely. The problem that we have, though, is that execution is volatile. The execution is tied to a process in an operating system, which is itself running on a piece of hardware. And so if the process where execution is running terminates, then the execution also terminates. And unless you've done something to maintain the state and progress of your application, that is lost. So if you write a program to count from 1 to 10 and the execution terminates as you get to 5, and then you restart it, what's the next number that's going to come out? 1. It's not going to start at 6 and go on to 10. It's going to start over at 1 because you've lost the state. You've lost the progress. You've lost the program counter that knew where everything was. So restarting an execution is a pretty poor means of recovery because you wind up executing things that had already run before. And not only is that inefficient, it can actually be dangerous. So if you think about, let's say you're trying to move money out of one account at a bank into another account at a different bank. So you do the withdrawal and then you need to do the deposit. If you're using a database, you have a transaction. You can ensure that both of these things happen exactly once or not at all. But you don't have that same sort of guarantee with execution. Yeah, I mean, there's distributed transactions. You can sort of simulate the kind of thing, but they're not really that common and they're not practical depending on what software you're using. But you don't want to do the withdrawal, the execution fails, and then you restart. So you do the withdrawal again and then do the deposit because the balances will be off. What you want to do if you're building a resilient application is you want to resume the execution. You want to pick up from where it left off as if nothing had ever happened. And so I want to take a quick detour and ask you about application design. Let's say that you're working at a bank or a financial institution, and they've decided that customers have to provide some identity information. Of course, they'll ask this on the application when you're applying for a new account. They'll ask this for new customers, but there's already a bunch of customers that are out there, and so you've got to collect this information from them, remind them to fill in their Social Security number, whatever it is. So we're going to write a simple program that's going to send a reminder to the customer asking them to provide this information. And then we're going to repeat that if they haven't complied. Every 30 days, we're going to send them another reminder up until a maximum of 10 reminders are sent. At that point, somebody's going to call them or show up at their house or cancel their account, or we don't have to worry about it after that. So to be clear, this program is only going to send out the reminders. We're not going to collect or store the identity information. That'll be handled by something external to us. And to make this easier, another team has provided us with 2 functions that we can call. So we don't even have to implement the thing to send the reminder or the thing to determine whether the customer has actually complied with the request. They provide those 2 functions. So how would you go about fulfilling this? How would you design this? Would you use a cron job maybe that runs every 30 days or a scheduler like Quartz or something like that? Yeah. Maybe you'd use a database to store the information about how many counts we've had, how many times we've executed this thing. Maybe you'd use message queues or something like that to send messages about everything that's happened. There's a bunch of different ways that we could accomplish it, but there's a much simpler way. We could just have a for loop, and then we could check if they've complied, and then we can send the reminder, and then we could sleep for 30 days, right? And everyone's laughing because you would never do this in production. If you submit this to your boss and say, here's the code, your boss would say, this is impractical. This could be running for potentially nearly a year, and there's no way you can be assured that the process is going to execute for a year, and therefore maybe it'll send one reminder, and then the program will crash, and then you're out of luck. But this is because of volatile execution. We can't do the simplest thing that would work because the execution is volatile. We have to maintain state, we have to write stuff to maintain state and use all these external systems to be able to do that. But this is actually the simplest solution that would work. And if you were learning programming, if you think back to, in college or high school, whenever it was you learned programming, this is what you would have done. But you soon learned in the real world, executions are volatile. You may not have been able to articulate that, but it occurred to you quickly, the program crashed and now the state is lost. So I would point out that if we can eliminate the volatile nature of executions and make them durable, then we can, in fact, do the simplest thing that would work, and it will work. So I want to propose or introduce a concept called durable execution. And that's a guarantee that the application is going to run to completion despite adverse conditions, whether they're based in software, whether they're based in hardware, the things that I mentioned before. This will allow us to achieve resiliency without having to accept complexity of all these external systems and cron jobs and sending state through message queues and whatever. There's a lot of different ways that you could achieve this, and people have tried it in different ways. One way is you could try to maintain an image of the memory and snapshot it, and every time there's a change in state in the application, you make a new snapshot. That is a pretty slow approach because memory gets bigger and it's a lot of data to manage. And also, if you have a program that's running for a long time, 300 days or whatever, you can't really make changes to your program because now the program that is in the memory is not the same as the one you're actually running. So that's a bit of a problem, versioning your code. But there's other ways that you can do it. So I'm going to talk about the way that it's implemented in Temporal. And I want to be clear, like this is not a product pitch. Temporal is a sponsor of the conference. I submitted the talk before the sponsorship occurred. After the talk was accepted, I said, hey, marketing people, let's sponsor this conference because it's an awesome conference. So I'm not here to pitch Temporal. I'm here to tell you about how durable execution is implemented in Temporal because I think it's a really elegant approach. When I first learned about Temporal, my first thought was, I don't believe this. How can you have this thing that can withstand crashes and hardware failures? I don't believe it. I will find a way to break it. And so I spent a couple days trying to find ways to break it. And I'm really good at breaking software, but I couldn't find a way to break it. And then I became intrigued to figure out, okay, how does it actually work? And when I discovered how it worked, which I will say wasn't documented all that well at the time, but I dove in the source code and figured it out, I was really impressed. It's one of the most elegant solutions I've encountered in software engineering. So that's what I want to talk about. I'm not here to like tell you the benefits of the product per se. But the way that Temporal is, to understand how it works, I do have to mention like what Temporal is. There's two parts of it. It's a client-side library, which we call an SDK. It's available in for 6 different languages. I guess .NET's not a language, a platform, but C#, F#, whatever. It's available for all those things. So there's a client-side library that you include in your application, and then there's server software that the client-side library communicates with to track the state of your application. I'll talk about how that works, but that's the gist of it. So Temporal automatically maintains the state of your application, and it recovers automatically from failure. So whether it's hardware, software, whatever, whenever the problem is resolved, it continues on, it resumes as if the problem never occurred. It also provides built-in support for managing retries and timeouts. Ultimately, what it does, I think, though, is it improves developer productivity because it makes applications easier to develop because you don't have to write more complicated code. You can do the simplest thing. It makes it easier to scale applications because you just run more copies of your application. You don't have to write a bunch of complex synchronization logic or anything like that. And it makes it easier to support because you can see exactly what took place for every execution after the fact, and you can debug things after they've already happened. But I want to point out Temporal is open source, released under the MIT license. And if you look at the license on our GitHub repository, you'll see 2 things. It says copyright 2020 Temporal Technologies. Well, that makes sense. Temporal is the company that's the majority contributor to the open source project. But then you'll see below that it says Uber. And you may think, what does that have to do with anything? To understand that, you have to look at the history of Temporal. So Temporal was founded in 2019 by Maxime Fative, who's shown on the left there, and then Samir Abbas, who's shown on the right. They had worked together previously at Uber, where they created a system called Cadence. Uber had switched to a microservices-based architecture, and as you can imagine, when you have thousands of microservices, trying to orchestrate calls between all those things becomes a challenge. And so they had built Cadence to solve a problem for their own team, but it sort of quickly took off among other teams because everybody was facing the same challenges. So it started getting used by other teams for their own applications. And Uber was Cadence was open source. So it started to be used by other companies outside of Uber. And those other companies, they started to want certain features. And because Maxime and Samer were working at Uber, they couldn't like go implement every other company's features. They had to do what Uber wanted. So they ultimately decided to be able to fulfill the needs of everybody who's not Uber, they needed to leave and fork the code base and create Temporal, which is what they did. And they added a bunch of features that weren't available in Cadence, extra security and so on. Support for new programming languages, that kind of thing. But going back even further, another 5 years before that, and actually a couple of years before that, they worked together at Amazon. And so Maxime was the tech lead and Samer worked on the team to create simple workflow service. And so these concepts that I'm going to describe, even though Temporal is relatively new, you could say, looking at the calendar, it's 5 years, it's actually a little less than 5 years old. You could say, well, this is pretty new and maybe unproven. Well, there's a ton of companies that are already running on Temporal. For example, if you know Snap, Snapchat, every Snap story runs through Temporal. If you know Coinbase, every Coinbase transaction runs through Temporal. If you know Twilio, every Twilio message runs through Temporal. That's key to how these companies achieve the reliability that they do. So there's already tons of companies running on Temporal, but the concepts that I'm going to show here sort of trace their way back to Cadence and to some work that, that Samer had done at Microsoft, which ultimately became the Azure Durable Functions, and then simple workflow service going back 15 years. So this is like a refinement of concepts that have been around for 15 years and are available in things that you may have used in the past. So you could say this is like a third or fourth generation kind of implementation. So the way that Temporal achieves durable execution, I'm going to go through the details in a moment, but I want to kind of give you an overview of it first. The first thing it does is it isolates the non-deterministic code in your application from the deterministic code in your application. The next thing it does is it uses event sourcing to maintain a complete history of the various function and method calls that you make. Not all of them, but the ones that matter to the state of your application. And it keeps track of the inputs and the outputs of each one of those calls. And upon failure, it uses that history, the result of all these calls, to reconstruct the state in a new process, and then it resumes the application. So I want to be clear, distinguishing this from the sort of let's make snapshots of everything that's in memory, which is a slow kind of approach and people have tried it, never really works out very well. Temporal does not try to maintain the entire state. It maintains the information it needs to be able to reconstruct that state, and it reconstructs that state completely. All the threads are there, volatile variables, all the values of all the variables, it's all there. Is the same as it was when it was originally running. It just reconstructs it through a method called history replay. And I'm going to explain how history replay works, but I'm going to kind of describe this in a few iterations, because if I was to describe this all at once, your head would explode. So I've got to give you a little bit at a time and keep sort of revisiting it. So I'm going to describe this with a specific example, like the world's simplest pizza order. Let's say that I own a pizza shop and an order comes in through my website. So the first thing I might do is iterate over all those different items to calculate the total price. You know, they had 5 pizzas, they're $20 a piece, $100. The next, and that's just simple arithmetic, you know. The next thing is maybe I call a service to determine if the address is too far away from my pizza shop. They've asked for delivery, and my pizza shop is in downtown Denver, and the customer lives in Albuquerque. I can't really deliver a pizza that far reliably, so I want to check the distance between my shop and the customer's address. The next thing, if that distance is too far away, maybe I say I only deliver within 25 kilometers. So if they're too far away, I'll return an error and we'll exit this process. But if they're not, if they're within the range, or if it's a pickup order and I don't have to deliver it at all, then I'm going to I'll cook the pizza, and then I'll call a service to bill the customer. So those are the 4 steps that we have. Temporal calls this sequence of steps a workflow. I want you to like cast any previous aspersions you have about workflow out of your mind. Like, workflow is a very loaded term. It means different things to different people. Sometimes when you say workflow, people think about we're drawing like little processes, or we're using, you know, we have to represent our business logic in JSON or XML or something. We can't use a normal programming language. The fact that it's called workflow is kind of a historical thing. I doubt if it was created today, it would still be called workflow, but it's When I say workflow, you should think durable execution. So it's a function that benefits from durable execution. This workflow defines the overall business logic, like the sequence of steps that you see here for processing the pizza order. The workflow is implemented as a function or a method, depending on which language you're using, and it's written in a standard programming language. You don't have to express your business logic in XML or JSON or whatever, and there's no limitations about having cycles. Anything that you can do in a programming language, you can do in a workflow. So you can write it in Go, you could write it in Java, you could C#, TypeScript, Python, or PHP. Those are languages we currently support. You could write it in any one of those things. I mentioned before that Temporal isolates non-deterministic code from the deterministic code. So if we were to evaluate this sequence of steps that we have, some of them are deterministic and some of them are not. So the code that is in the workflow, all of it must be deterministic. That means that we can't do things like call a network service or query a database or read or write to a file. All of those have the possibility of failure. It could be that the file permissions don't allow us to read or write to the file. The database maybe is unavailable, or we have the wrong credentials and we can't connect to it. We don't have access to view the data. It could be that we're trying to call a network service, but the network's down, or the service is down, or it's overloaded and can't respond. So all of those things are non-deterministic because they include the possibility of failure. We're doing something external. There are side effects, in other words. So fortunately for us, we can still do these things. It's not like, well, temporal workflows can't query databases. They can't, but they can call functions that do those things. So all we have to do is separate out the non-deterministic code into a separate function or method. If you're using Java or object-oriented language, you just put it in a separate function, and that thing we call an activity. So the workflow is the deterministic code here's the entire sequence of steps, and any non-deterministic steps that you might have, that code goes into a thing called an activity, but they're both just functions. Those activities are automatically retried upon failure, and you could actually write each activity in a different programming language, and that could be different than what the workflow's in. So polyglot programming is possible. You could write the workflow in Go, and you could write the first activity, it could be in Java, and the next one could be in Python or whatever. It makes it very easy to collaborate on teams that are using different languages, but you can definitely do that. So once we isolate out that non-deterministic code, we put those into activities, as I mentioned, and those simply get called during the execution of the workflow itself. So the workflow can pass, just like you can pass data to a function, and you can get the result of a function when you call it. Same thing here. You can pass input data from the workflow to the activities. When the activities produce some sort of result, like whatever the microservice that you're calling returned, it can return that to the workflow, and the workflow can evaluate it and do whatever it needs to do. So that's the gist of it. Make sense so far? Okay. I mentioned that activities are automatically retried. Well, since they encapsulate the business logic that is prone to failure, making network calls, database queries, writing to files, that kind of stuff, those imply the possibility of failure. So if it does fail, then it just retries until it succeeds. So the default behavior of an activity execution is try this thing, and if it fails, retry it again. By default, it'll retry it after 1 second, and then it'll double it. So 2 seconds, 4, 8, 16, and so on, till it gets to the maximum of 100 seconds. And then it will just keep trying it forever until it succeeds or until you cancel it. But you can customize that behavior. As you can imagine, if you're trying to call a microservice that is billing you every time that you call it, you don't want to just retry infinitely because you could rack up a big bill. Or maybe you want to have a longer delay between each try. That you can totally do that. You just override some attributes in the retry policy. So I've shown an example here of a retry policy. I've included it here because it's not in the code sample that I'm going to walk through. Just if I would have included it, it would have made the font so small that it'd be hard to see the code that I'm going to show you. So I put it here to illustrate the point. This is declarative. You don't have to write your own code, your own for loops, and your own timers to manage the timeouts. It's all done for you. You just say what it is you want. So here's an example where we say, we'll wait for the first retry, we'll wait 15 seconds, then we'll double it, and then when we reach the maximum of 60 seconds, we'll stop there. Each subsequent retry will be 60 seconds, and we'll give up after 100 attempts instead of doing it forever and ever. So that's an example of how you can customize that behavior. So now I want to talk very briefly about the architecture so that the walkthrough of the durable execution will make sense. There's two parts of it, as I mentioned. There's a client-side library, and then there's a service that is tracking the state. And so that's the temporal service. It manages and tracks the tasks related to your workflows and your activities. So it is a task manager, and it maintains and it durably persists the event history. So every invocation of the functions, your workflow and your activity functions, it keeps track of those, when they were called, what they were called with, whether they returned successfully, whether they failed. If there's retries, it keeps track of that. What the value was that they returned. If they failed, what the error message was. It's keeping track of all that information. But importantly, it does not run your code. It doesn't even have access to your code. If we look over here, the other side of the equation is what we call the worker. This is the thing that actually runs your code, and it's distinct, separate from the temporal service. They're typically not even running on the same computer. They could be in entirely different data centers. So the worker is running your application code. The worker is provided by the temporal SDK, but it's something that you configure, and you configure it to say, here's the host name and port number for the temporal service. You have to configure that, and you have to tell it the name of the task queue that it should use for your application. And there's a bunch of performance tuning related things you can set, but you don't have to. So there's a minimal configuration that you need to do, but the worker is the thing that runs your application code, your workflows and your activities, and behind the scenes, it communicates with a temporal service. And it's reporting the status. It says, hey, I'm going to work on this. Here's the result, or it failed, here's the error. The temporal service will put things into the task queue that then the worker will pick up and know what the next step is to do. So I wanted to demonstrate this now. I'm not going to show you the code. I'm just going to run something and run the example so you can see kind of the outside, what things look like from the outside. Then I'm going to walk through the code to show you what it looks like from the inside, what's actually happening behind the scenes. So this is the pizza order. Unfortunately, there's no actual pizza here. It's all virtual pizza. Is this terminal window big enough, easy to read from the back? Another, yep. How's that? Ah, so much easier with a mouse. Okay. So there's three parts of this. The first thing I need to do is start the temporal service. And so you could run the temporal service. You could run it on a laptop, as I'm going to do here. This is like a tiny little development instance that runs everything inside a simple, in a single process, and it has a built-in database. That's not what you would do in production, but it's good for development. In production, you could either self-host the service on as many services or servers as you want, or in a cloud provider. Anywhere you want to put it is fine, but it scales out across multiple machines. And then we have a cloud service that it's a managed service, so you don't have to run your own. But I'm going to demonstrate this here. So temporal server, start the development server. Boom, it's up and running. Now the service is running, and I can do the durable execution. So the first thing I'll do is, or the next thing I'll do is I'm going to run the worker for my application. And it's just sitting there. It's pulling the task queue, saying, okay, what should I do? What should I do? So the next thing I need to do is actually give it something to do. So I need to start the workflow. I need to submit a request for pizza. And so I've written a small program here that will submit that. And the code's not really important. It's just basically I create a data structure of a bunch of pizzas, like a large pepperoni pizza and whatever, and then I'm submitting a request to the temporal service saying, run this workflow. That's all it's doing. So I run this, and now if we switch back over to the worker, I don't know what that, had a spare tab there. I'm going to kill this. Okay, so I'm going to show the logs. So the first thing that it did is it ran the, we can see where it called the get distance function. So it's calling the service to get the distance. And then it's the distance return 20. And now it started a timer, says go prepare the pizza. So now I got to pop the pizza in the oven and deliver it to the customer. But it has not yet called the thing that bills the customer. So I have terminated the execution. I've terminated the process where the worker's running, but I have not terminated the execution because the execution can span multiple processes, as I mentioned. So now I'll run this, and it's going to pick up where it left off. And now it sends the bill. Notice if you look through that log, it's not trying to get the distance again. It's not running the timer again. Those things have already happened. All it's doing is sending the bill. And if I switch over to the terminal where the thing is running, then we can see the output and the thing completed successfully. So that's what it's all about, the durable execution. Now let's look at how that actually works. So the code that you write, there's certain things that happen in your code when you make certain API calls, like I want to execute an activity, that result in a command being sent from the worker to the temporal service. And so if it runs across a line that says workflow.execute activity, then it sends a command that says schedule activity task. The temporal service puts a task in the task queue saying, we need to run this activity, and then it also logs an event to the history that says this task has been scheduled. A worker then goes and picks up that task and then runs the function. So here is the code. This is actually pseudocode. I've simplified some elements of the Go syntax just to be slightly less verbose, so the font is a little bit easier to read. But we define a timeout for the activity execution to say that it can't last any longer than 5 seconds. That's like line 4, maybe line 3. Then we iterate over the data structure, the orders data structure. We calculate the total price of the pizza by just creating a sum of each individual pizza. Then we call the service to figure out the distance to the customer. If it's too far away, we fail. Then we sleep for 30 minutes. Then we populate a struct with the information about the billing for the pizza order, and then we send the bill to the customer by calling the service. So some of these steps are internal to the workflow. That is, they don't require any interaction with a temporal service. Others do. For example, if we're setting configuration parameters or we're doing the basic arithmetic to determine the total price of the pizzas, that does not need to call the temporal service. If we're just doing a calculation, if we're evaluating a variable, we don't need to call the temporal service because that's not really important. If we're populating data structures, again, no interaction with a temporal service. So I've highlighted those kind of internal steps there in white. Other steps that we do involve interaction with a service. So if we execute an activity, or we set a timer, or we return an error from the workflow, or we return a value at the end of the workflow when the execution is successful, those wind up sending a command to the temporal cluster, and I've highlighted those in yellow. So just walking through the code, the first stuff that I have here, which is highlighted in white, that's all internal. Then we get to where we're going to execute an activity. So this results in a command, schedule activity task, that has the details needed to complete that thing. And then some tasks will get queued, the worker will pick it up, and the workflow execution will continue. And then we get to where we're going to start a timer, another command, start timer, with a duration of 30 minutes to allow us to cook the pizza. Then we populate a data structure, internal step. Then we get down here where we say we're going to call another activity to send the bill, so we have another command there. So, and then when we get done, there's a command that says we've completed the workflow execution and here's the result. So all of that is just what's happening behind the scenes. You're writing workflow code that just looks like, Go, or in this case, or whatever language you want. You're making a few temporal specific API calls, but behind the scenes, it's sending commands to the temporal cluster. So here's how the history replay works. We start the workflow execution by calling client, with a temporal client, we call the execute workflow function, and we pass in the input data and we tell it what workflow we want to run. So pizza workflow is the one we want to run, and we give it the input. The input, here it's rendered in JSON format, and so that is what gets passed. And when that happens, the temporal service, after receiving that request, it logs an event workflow execution started. So this workflow has now begun. And the next thing it does is it queues up a task to begin executing the workflow, and it puts it in the task queue, and it logs a workflow task scheduled event. The worker, because it's looking for something to do, the worker polls for the task, and it says, hey, got anything for me to do? Temporal service says, yep, got a workflow task. So the worker dequeues that task, at which point the workflow task started event gets put into the event history, and the worker will begin running the code in the workflow function. So it invokes that, it runs the first few lines, and it keeps on running stuff. It's calculating the price of the pizza, all those internal steps that don't require any interaction with a cluster. It's doing all those things. Eventually, it reaches a point where it can't do anything more because now we're awaiting the execution of this activity. So it says, I'm done. A workflow task completed event is added to the history. A command gets put, the worker issues a command, schedule activity task. So the temporal service logs an activity task scheduled event, and it creates an activity task, puts that in the queue. And now the worker will go pick up that activity task, and it's going to invoke that activity. I don't have the activity code here, but it's just imagine that's some other function, and it executes that. When it's done, it says, okay, I'm done with that activity task. The server, the temporal service puts activity task completed, and it also stores the result of that. Let's say it's 15 kilometers is the distance to the customer in this case. And it puts another workflow task because the workflow is not complete. The worker picks that up, begins running it, and it keeps running stuff until it finds another thing that requires some interaction. In this case, we're going to set a timer. So it sends that message that we're done with this workflow task, and it sends a command, start timer for 30 minutes. So it just sits there waiting. There's no new task getting queued for 15 minutes, or I'm sorry, for 30 minutes. And at the end of 30 minutes, when the timer fires, then a timer fired event gets put into the event history, and a new workflow task gets queued. The worker polls for the task, picks it up, begins running the remaining workflow code. And let's say the worker crashes right here. Well, first, how do we know that the worker crashed? Because it didn't respond quickly enough. So there's a workflow task timeout, and if that is exceeded, then the temporal service assumes that that worker has crashed and has gone away, so it puts a new workflow task in the queue. It's rescheduling that task. And another worker picks this up, and it dequeues it. It says, hey, I don't know, this is already in process, so I need the event history to know how I can reconstruct the state of this existing execution. So it gets the execution history, and it starts running the code again. And it gets to a point, it's just executing this code just like it did the first time. Eventually, it gets to a point where there's some interaction with the service. So here we have the command, and it says, do I need to send this to the temporal service? Let me look in the event history. Well, activity task scheduled was called for the get distance activity. So this thing was invoked before. The worker picked it up because activity task started is there. Did it return anything? Yep. Activity task completed is there, and the distance it returned is 15. So we don't need to run this again. What we can do is substitute the function call by assigning the value of the previous execution. And it says, not going to send this command because this is something that's already taken place. It keeps running the code. It reaches another point where there's another command. It evaluates the event history to see if that thing is run. Yep, timer started is right there. Timer fired. Okay, well, that's already done. Don't need to do this again. And now we reach the point at which the error had, the thing had crashed before. So we've reconstructed the state of everything. If you look back to where we calculate the total price of the pizza, this code is run before. It's deterministic, so we can safely rerun it again. It's only the stuff that is non-deterministic that we can't run again. But because we've substituted the results of the previous execution, it's able to completely restore the state. And so eventually we get down here and we just continue running things as if the failure had never occurred. So it says, do we need to issue this command? Looks in the history. Yep, this thing had never run before. So let's issue that command. So now we have an activity task. The worker picks it up, dequeues it, begins running that stuff, says we're complete. and that activity task is complete. But because we haven't returned from the workflow yet, there's still a little bit of code left to run. It puts a new workflow task in there. The worker picks it up, begins running the remaining code in the workflow, and now we've reached the end and we return the result. And that is another command, complete workflow execution, that contains the result of this function. And when we send that to the temporal service, it says, okay, workflow execution completed. So it now has a complete history of everything. So to wrap it up, the executions that we typically work with are volatile because they're tied to an operating system process. So when that process terminates, the state and all the progress are lost. And restarting is a poor substitution for being able to resume. If we want to build a resilient application, we need to be able to pick up where we left off as if the failure had never occurred. We can do that with durable execution because it guarantees that the application will run to completion no matter what happens, even if it's a hardware failure. As I've explained, Temporal uses event sourcing to implement durable execution. It isolates the deterministic code from the non-deterministic code, and it uses history replay to reconstruct the state based on that history and resume the execution. So that's it. Okay. And I've taken up the full 45 minutes, so there's not time for questions in this room, I don't think. But I'm going to go to the table that's just outside the door. There's a Temporal booth out there, and if you have questions, I'll be happy to answer them there. Thank you all for coming.